Hello, welcome to my lecture. Today I'm going to give a lecture about classification of signals. First, I'm going to give introduction about signals. In this lecture, I'm going to know about what is a signal, what are the types of signals, and what are the signals day-to-day life we are experiencing. First, we are going to see what is a signal definition. A signal is nothing but a physical quantity which varies with respect to any one of the independent. Mostly, we are taking the independent variables time. Here, if you see the definition here, a signal is a function of one or more independent variables that carries some, that conveys some information to represent a physical phenomenon. The example for signals are ECG, EAG, speed signal, audio signal, video signal. These are all comes in your signals, and there are many signals out there. If you take mainly, there are two types of signal. The first one is continuous time signal. Second one is discrete time. First, we are going to focus on continuous time. Continuous time. In continuous time signal, the signal has value for all points in time. For every value of time, there is a certain amplitude is there. And the amplitude is continuous, and even time domain is also continuous. And this continuous time signal, it's a function of time. In continuous time signal, we're taking the independent variable is time. Always here the amplitude varies with respect to independent variable time. And we are going to write the signal as x of t, and that in the y-axis. And time in x-axis, we are going to take time t as an independent variable. The commonly found signals in the physical world are human speech. And if you see the graph, x of t representing y-axis and time t in the this is about continuous time. Continuous time signal always signal is going to vary with respect to time t. The signal is available, amplitude is available. Amplitude we are taking the y-axis and time t on the x. That is about continuous time. Continuous time signal is continuous as well as your time domain is continuous. Second one is discrete time signal. The name itself it is there. Here the time domain is discretized. And signal amplitude is not there for all the values of time. In the previous one, continuous time signal, the signal is available for every value. But here the signal value, signal amplitude is available only for discrete instance. Only discrete values of Vn. Only the signal is available. When you apply sampling operation over the continuous time signal, we'll get the discrete time signal. For sampling operation, the input is continuous time signal x of t. When you apply sampling operation over it, you will get the discrete time signal as an output. And here, this discrete time signal, we are denoting with, we are representing with x of n, and xx we are representing with the time index n. The commonly found the signal in digital world is wave file or MP3 file. Here the signal value is available only at the discrete value. And you can see the graph. This graph we are used to call as stem plot. And that's about your discrete time signal. Discrete time signal, the amplitude is continuous, but the time domain is discretized. That's about discrete time signal. This gives the clear example of continuous time signal versus discrete time signal. The first graph I've taken here, a sinusoidal exponential signal which is decaying with respect to time t. X of t is a continuous time signal and it is decaying, it is decreasing with respect to time. That is about continuous time signal in the left hand side. And if you see the signal on the right hand side, that is a discrete time signal. That one we are denoting with x of n. Time index we are taking here. Here the signal value is only available at discrete instance of time. Next one is sampling operation. We are using sampling just to convert your continuous time signal into discrete time signal. For sampler, if you see the black diagram, we have sampler. For sampler input is x of t, that's a continuous time signal. When you apply that x of t to the sampler, you'll get x of n. That is about sampling operation. Next one, we're going to see some standard signals. What are available in the signals? The elementary signal, the basic signal, the standard signal. So first one is I'm taking here unit step signal. That one we are representing with u of t and its value is 1 for all positive values of t. From 0 to infinity, the unit step signal value is 1 and is 0 for negative values. And we show the graph here. And if you see the graph, it's continuous for all positive values from 0 to infinity. Its value is constant. Its value is 1. For all negative values of t, the signal is 0. Next one, the same signal, unit step signal. If you take a discrete time, that one we are denoting with u of n, and u of n value is constant, and its value is 1 for all positive values of n. For 0, 1, 2, 3, up to infinity, its value is 1. For all positive values, its value is 1. And for negative values, u of n is 0. That's about unit step signal both in continuous time and discrete. Next one is unit ramp signal. Unit ramp signal usually we used to represent with r of t or ramp t. And ramp t here, the mathematical equation is t, ramp t equal to t for all positive values of t. For of all positive values, the signal linearly increases with respect to time. For negative values, the ramp signal is 0. That's about your unit ramp signal. When you do integration over the step signal, you'll get unit ramp signal. Similarly, if you take a differentiation over the ramp signal, you get the step signal. That's about the relation between step and ramp. Next one is unit impulse function. And this is a pulse which is there between minus a by t, and its value is 1 by a. Next one is unit impulse function. That one we are denoting with delta d. And this is valid only at t equal to 0. When its strength or right value is equal to 1, that one we are calling as unit impulse. Next, unit impulse time, it's a combination of unit impulses. And its mathematical equation is delta t equal to summation n equal to e minus infinity infinity delta t minus here n is an integer value. Next one is sinusoidal and exponential signals. This sinusoidal and exponential signal in continuous time domain. We take the first signal, sinusoidal signal, and its mathematical equation is equal to a sine omega naught t. Here omega naught is a signal, omega naught is a frequency in radians per second. Same omega naught we can represent as 2 pi f naught, and that is equal to 2 pi by t. Here f naught is the frequency, t naught is your time period of sinusoidal. Next, exponential signal. Here we have two types of exponential. One is a real exponential, another is complex exponential. Real exponential mathematical equation is x of t equal to a into e power at. Here a is the amplitude, a is the real number, small a is the real number, and here small a, there are two possibilities are there. When a is greater than 1, your exponential signal is increases, it's a growing, and when a value between 0 and 1, it's a decaying signal. Second one is complex exponential. Here also x of t mathematical equation is a into e power j omega naught t. A power j omega naught, we all know that it's nothing but cos omega naught t plus j sin omega. It's a combination of cosine signal and sine signal. And theta is the phase here. This is the graph. Here we have 4 graphs. The top left and right signals are exponential signal. First one is a decaying exponential. There a values between 0 and 1. Second one is a rising exponential. That there a value is greater than 1. And next one, third signal is a decaying sinusoidal signal. There r value is less than 0, and last one is growing sinusoidal signal where r value is. Next is signum function. Signum function value is 1 for all positive values, and signum function is -1 for negative values, and signum is 0 for at t equal to 0. That is about signum function. That one we are representing with Sn of t, and this is closely related to the unit step function. This is a combination of two unit impulse. One is positive impulse and negative. Next one is a rectangular pulse. Rectangular pulse we are representing with delta at, and its value is equal to 1 by a. Between minus a by d to a by d. That is about your unit rectangular function. Next, unit triangular function and its values boundaries are between -1 to 1, and we are representing with triangular. Next is sinc function. Sinc function mathematical equation is sin pi t by pi t. And when you take the rectangular pulse Fourier transform, you get this. Next, discrete time signal. We all know that how you get the discrete time signal. When you apply some sampling over it, then you get the discrete time. Now we are going to, till now we seen all the basic standard signals in continuous time domain. Now we are going to see the discrete time signals. And here, for first one here I'm taking is sinusoidal signal. That one we are representing with x of n equal to a sine omega naught n plus theta. And second one exponential signal. Mathematical equation is x of n equal to a pole. Here a is a real number. Based on a value, there are two possibilities are there. When a is greater than 0, it growing signal. When a is between 0 and 1, it's the decaying signal. Next one is in discrete time domain, we have unit step function. Unit step function is 1 for all positive values of 1. This one we are mathematically representing with u of n and its values 1 for all n greater than equal to 0. And u of n is 0 for negative values. This one we are calling as a causal example for causal signal, which is defined only for positive values. And you can see the graph. And next one is the ramp signal. Ramp signal we are denoting with the ramp n, and its equation is, ramp n mathematical equation is n for all positive values of n. For negative values of n, ramp is 0. It's linearly increases for all positive values of n. That is about ramp signal. Next one is unit impulse function. This one we are denoting with delta n. Delta n is defined only at n equal to 0. For all non-zero values, the impulse function is 0. That is about unit impulse. Thank you. Thank you.